Welcome to my talk. Yes, the topic of my talk is the model PALM. PALM is a large eddy simulation model, and I would like to give you a short summary of the story of how to develop and maintaining a scientific code like PALM. So first, what is PALM? PALM is a large eddy simulation model, so it's a CFD code, and we can simulate dust devils, wind energy, aviation, urban meteorology and city planning, cloud physics. So basically, we simulate the atmosphere within the lower few hundred meters to 1 to 2 kilometers above the surface. And everything what is in there is simulated by PALM. So then what does PALM in the what does PALM on the within the base of the code? So we solved the Navier-Stokes equations, which I think every CFD code does, and we solved it on the Cartesian grid. And then we have within the code we have numerous different numerical schemes. For example, we use a third-order Runge-Kutta time-stepping scheme. We use a fifth-order differencing advection schemes. We have a pressure solver. We have even different pressure solvers, an FFT solver and a multigrid solver. And we also use a lot of different other numerical codes and schemes. To run PALM, we use a 2D domain decomposition realized using MPI. So if you think of this block being the atmosphere, then we divide the atmosphere in these vertical columns, and then one core, one CPU solves all the equations within this core, and then we use MPI to communicate between the different cores. But that's not all. We also use OpenMP and OpenACC for parallelization within one of these columns. So we try to use everything we can to get the code parallel and quite fast. And we also achieved a quite good scalability. We tested this with up to 40,000 cores, and this is the graph. So it scales quite well, I would say. So these are some facts. Now, to give you a little bit more of a nicer introduction to PALM, I would like to show you a short video. And there are also other videos. We have a YouTube channel. You can go there on YouTube and have a look. But now, so what does PALM? So it is from the Institute of Meteorology and Climatology in Hanover. And for example, we can simulate dust devils. Dust devils are like these little guys in the atmosphere, where we can simulate the dust whirling around in eddies. We can also simulate shallow cumulus clouds and the interaction between the clouds and the surface above, below the clouds. We also can simulate the cloud particles with a Lagrangian particle model. We are able to simulate wind turbines and the turbulence around these. Can I go any faster than this? I guess not. Okay, so basically we can do a lot of things. And this is then the first challenge of maintaining the code. So in this graph, I tried to put everything we can simulate with PALM, and I guess I even missed some things. But to name just a few, we can, of course, simulate the general dynamics, so the wind speed, so the wind through the atmosphere. We can simulate the buildings, so we can resolve the buildings, which is not always the case with every CFD code. We simulate the radiation effects. So we have actually a sun in our simulation, which shoots the rays through the city. We can simulate the chemistry within our within the atmosphere. We can simulate we have a soil model, so that we also simulate how the temperature and the humidity or the water goes into the soil and also out of the soil into the atmosphere. We simulate the plant canopy. So we have a plant canopy model. So we have actual trees in our simulation, and we have the interactions between the trees and the atmosphere. Of course, as we do meteorology, we also have the clouds and also rain. Unfortunately, no snow, but this will come soon. We have a Lagrangian particle model, which is a large model by itself, but it's also implemented into PaLM, and it's part of PaLM. We have a multi-agent model. This means we can simulate people running around our city or within the atmosphere and have the effects of wind and temperature and humidity on the people. We have a wind energy model, so we also can simulate the energy gain from wind turbines and also the turbulence effect of a wind turbine into the atmosphere. We have a flight module, so we do not simulate actual planes, but we can simulate flights through the atmosphere and measure data along the flight path. And we also have an ocean model, so we can switch the model, and then we do not simulate the atmosphere anymore, but we simulate the ocean, which is basically the same with a different density. So we have a large list of features in the code, and this is also the first challenge, the code base. We have an ever-growing list of demands for new features. Although we already have a lot of features, there are still new features which shall be implemented. This is a very big challenge. Then we have to deal with legacy code. So our code base is already over 20 years old, but it's still lively, it's still developed further, but parts of the code are already over 20 years old, and they could be improved maybe in some places. Then it is quite fast growing in the recent years. This is also a big challenge of the code base. So this is a graph showing the total files within our repository. So it starts at 2008, and recently, so within the past 1.5 years, the number of files went up from about 2,000 to nearly 6,000. So the code base is very fast growing. The number of commits within our code base is also quite growing, and also within the past 2 years, it's even faster growing. Also, the lines of code is also quite interesting. So we started with about 50,000 lines of code, and now we are nearly at 250,000 lines of code. So it's quite a large code base. And this now brings me to the next challenge, the performance and the parallelization of this very large code base. So we already have a good performance, but when we implement more features, we have to keep this performance. So to do this, the new developed features must support the parallelization. And this means the new features have to support MPI, OpenMP, and also OpenACC. And this is a big challenge because the developers who develop all the new features, they have to be familiar with the parallelization techniques in order to keep the performance and to keep PaLM as good as it is now. Then this brings me to the next challenge. Not only the code base is a challenge, but also the developers themselves are a big challenge for the sustainability of the code. So PaLM is usually developed by a team consisting of scientists rather than trained software engineers or software developers. And this is a picture of our group there. So this means, as we are now, as we do not come from the computer science, modern software development methods and tools are mostly unknown to us. We are metrologists and we do not know anything, or well, we now try to learn something about unit testing and all these things, but they were unknown for us for quite a long time. So, and this brings me now to the solutions. We try to tackle these challenges, or at least our approaches to the solutions. So there are many approaches. First is the coding standard. We implemented a coding standard for our code. We have now an internal performance monitoring. We use a Jenkins test server and CI pipeline. We have a user documentation and tutorials for the user. We have a feedback system via a issue tracking system on our website. We increase our performance know-how by joining hackathons, GPU workshops, CPU workshops, computing conferences. We also have internal Palm workshops to train first our own team and then also our users how to use the code. And a big thing which we are now currently doing is we make a design rethinking in refactoring. So we try to make some change management in our code base. So I will now go into more detail in some of these points. So first, the coding standard. We have a coding standard. It's a list of rules with examples to ensure a unified code structure. So we have different developers, and they all have their kind of how they write the code, and that our code base is somehow homogeneous within through all the whole code base. We try to teach our developers to code after certain rules. So we have a Palm coding rules. They are quite elaborate. It's a list of rules how to write code, and this is all available publicly at our website. So every developer can have a look at it and should also code after this coding standard. Then we have an internal performance monitoring. This means we have runtime measurements specified in around some code parts. And I think I didn't mention, but as you might see, we use Fortran code, and we use some own subroutines to measure how long certain parts of the code are taking to execute. And after each simulation or each run of the code, we have an output into a monitoring so-called monitoring file, where we list all the runtime of all the different parts of the code, so that we always can monitor if some code parts are getting slower and slower while the development is moving on. Then we also used a Jenkins test server. So I think most of you already know what Jenkins is, or what the Jenkins test server is. It's an automated testing with a Jenkins server. And we introduced this only in 2017, although the code development started in 1997. So after 20 years, we finally have some testing, automated testing. And now we also give the result of the testing of the test on our website, so that everybody sees if the code is broken or not, which is also something quite good for the developers, so that they see that they try to be good in developing and that the code does not break. But the codes have to cover the entire code base, and this is still not achieved. We are still trying to cover most of the code base, but this takes some time. And you also have to train the developers to actually use the tests and also to develop new tests. So At the moment, it always it happens quite frequently. So maybe once every 2 weeks that the build does not pass and it's failing. This is because our developers are still not that familiar with how to use the test server in advance before submitting to the trunk, so to the official code base. Then we have an issue tracking system. So on our website, when you log in as a user, you can submit an issue or a ticket, and then we try to figure out what the bug is, or if there's a bug, or if the user just doesn't know how to use the code, then we have to fix the documentation, of course. But then there's another problem. As Palm is getting more popular, also the number of tickets is rising to a quite high number. And as we are a small development team, we have to try to keep up to the number of tickets. Then hackathons and internal workshops. So we always try to get more involved in the software development within our team. So we attend hackathons to improve our code performance, and we also hold seminars to train our users and also our development team internally. So we give, I think, almost twice a year now, we give a so-called Palm seminar to train our developers and also our users. Okay, and this already brings me to the summary. So what I showed is we have a highly complex simulation model. It has many features and is highly performance optimized. This brings a high demand of sophisticated development methods and tools, and also the training of the development team and also the users, unfortunately, is necessary to correctly use this very complex code. Then we also have the problem of the development team that it has less to no IT background, and this this gives that the solutions to problems are often far from ideal, which we use, and the modern development methods and tools take quite a long time to be adopted to our working flow. For example, as I mentioned, the automated tests took over 20 years to be used somehow, or any tests to be used. So, and this brings me already to my end. So thank you for listening, and if you have any questions or comments or suggestions, what we do wrong or what we can improve, then I'm very happy to hear your thoughts. Thank you.
Yeah, thank you, Tobias, for this clear talk. I recall my suggestion that we postpone discussion about the management and maintenance aspects to the end of the session. And now, are there questions regarding the application, the technology?
I don't know, probably I might forget my question, so I ask it now. So you talked about those tickets, and you had accepted tickets. So what is this?
The accepted tickets, they are just, this is some feature of our server, of the track system we use on our server. You can assign it, or you can write a ticket as a user, then it is on the website, and as long as no developer is assigned to the ticket, it's not assigned, or it's, so it's just an open ticket. And for a long time, we did not assign a specific developer to this ticket. So this is why this red line is quite small. But usually those two lines should be on the same level, and they are normally.
Further questions? Up there, maybe? No, I try to understand and then I repeat.
You said that you are using Cartesian grids, and you are using advanced methods. I'm interested in, do we use uniform Cartesian grids or unstructured, or non-uniform Cartesian grids? Because the problems that you show would rather benefit from unstructured.
Yeah, I repeat the question. Yeah, thank you. I repeat the question for the benefit of the video streaming. So is that a uniform Cartesian grid, or is the grid adapted to the structures at the ground?
We use a uniform grid. We use a rectilinear grid. So it is stretched along one direction, along the Z direction. But in X and Y, we have a fixed distance between the grid points.
And I have a related question. In the beginning, you showed simulations at different scales, building up of clouds over a vast landscape, and then wind blowing through a street. These are different scales then. It's the same physics, the same partial differential equations, the same algorithm at these different scales?
Yes. It's always the same algorithm at the different scales. What we change is just the grid size. And usually, well, in this simulation, for example, where we simulated a dust devil, we have a grid size of 0.1 meter, I guess. And then in other simulations where we simulate clouds, if we only simulate one cloud, then we might also be in the size of 1 meter. In this simulation, for example, we have a grid size of 25 meters. So we then adopt, or we use a different grid, so to say, so a different grid size, and then we can cover the different scales of the simulation.
And when it then comes to urban climate, where do you take your ground model from? Do we have a database with all the houses in the city?
The database is the big issue there. Right now we have a quite large project running, or actually it was running until the end of May, where we got all the data from all the different people who own the data. So we got the building heights from the ministry. We have some other colleagues getting all the data of the trees, for example. Then, this is a nice example for here in this simulation. We also had the data for the wall materials of the buildings, and this was a research topic itself to get all the wall materials of the buildings, for example. So getting the data is, or the starting point of the data is always quite a challenging task, and this is case specific then.
Yeah, thank you. Any more urgent questions? Yes. Maybe we come back to that at the end and discuss that with all speakers.